So determination of volumetric properties. Once we've decided on 3 trial blends, we're going to actually take those into the lab, produce those mixes, and see what kind of volumetric properties they give us. One of the first things we have to do is decide what binder to use. If we're doing work for the federal government, say you're doing a Skyline Drive or Parkway, you're going to have to look in the specs to determine, based on the traffic, based on the wrap, what kind of binder you use. For VDOT, it's much simpler. The department's going to basically tell you in the contract which mix you're going to use, and that's going to tell you based on specs, based on how much wrap you're using, what binder you're going to use for that specific mix. So we're going to estimate asphalt binder content for each of the trial blends. We're going to mix and compact those trial blends through the gyratory compactor. We're going to evaluate the trial blends volumetrically, and then we're going to select a design aggregate structure based on the asphalt content and which of the volumetrics we think is going to work best. So estimating trial binder content, this is going to be based on experience. We're doing an SM 12.5 mix. It's a surface mix, so what should the binder content be? I recommend doing this based on experience. You can always call the department, ask them what the typical 12.5s look like in that vicinity, in that area with those materials. Another way you can do it is also refer to AASHTO R35, which is a federal specification. It takes into account the materials that you're using, the absorption of those materials, the gravity of those materials, and will actually give you a mathematical formula to calculate what the estimated asphalt content would be. I would highly recommend just go on experience, base it on speaking to others and finding out what a typical asphalt content is for that mix. In this case, we're going to use 5.5% for this 12.5 millimeter mix. So the required testing is we're going to do 3 gyratory pills for each of the trial blends. We're also going to do 2 rices at 2,000 grams apiece. Now these rices, we're not going to do a single batch and split it. We are going to mix 2 separate samples for those rices. So the total number of samples, we're going to have 9 gyratory pills, 3 for each of the trial blends, and 6 different rices, 2 rices for each of the trial blends. So mixing and compaction temperature, there are mixing and compaction temperatures depending on what type of mix that we're using and specifically what kind of binder that we're using. Section 211, D6 refers to, for mixes designed designated A mixes. Our mix temperature is 300 to 310 degrees and our compaction temperature is 285 to 290. What you'll find is that mixing temperatures actually have to be a little bit more, and you are allowed a little bit more as per federal specifications. You can get up to about 340 degrees. You lose a lot of heat when you mix these batches in the lab, and the key is we want to be at compaction temperature, which for A mixes is 285 to 290 degrees. I also recommend that you try to hit the same side of that range just so that you're consistent when you're doing these. D mixes, as you can see, the mix temperature is specified at 310 to 320. The compaction temperature is 295 to 300 degrees. For mixes that use polymers or E-mixes, modified binders, you're going to want to use your manufacturer's recommendation both for your mixing temperature and for your compaction temperature. Required aging is a key component of mix design. When we make mix in the field, that mix is put into a silo typically where it may stay anywhere from 30 minutes to 2 days. From there, it's going to be loaded into a dump truck and it's going to be hauled to a job site. You know, you may have a 30-minute to an hour haul there. From there, it's going to be, that truck is going to pull into a queue into the construction zone. He may sit for 15 to 30 minutes there before he's actually unloaded into the paver and it's actually laid with the machine. During that time, a lot of absorption takes place of the liquid asphalt into the aggregate. And that's exactly what we're duplicating when we age material in the oven. So we're going to age material according to R30, which is a federal specification, for 2 hours, plus or minus 5 minutes at the designated compaction temperature for that mix. This is done for both the rice sample and all of our pill samples, all of our gyratory samples. We do not do aging for production samples. Here is a chart right out of the federal specifications. This is FHWA. You do not need to memorize this. It is important to note that superpave specifications at VDOT really started, they were spawned out of the FHWA specification. So if you are doing a parkway job, if you're doing something for the federal government, you'll notice that the specifications are a little bit different. VDOT has subtly changed the specifications. They've evolved over the years to what works well for Virginia's materials. Here is another FHWA design criteria. This talks about basically your minimum VMAs, VFAs, and FA ratios. And here is section 214 of your mix design criteria. Some of these have changed. I think your 9.0 mixes are also 50 gyrations now. But this is basically our cookbook. This is where we determine what our production VTM is, what our design VFA, minimum VMAs, which is extremely important, and also our fines to asphalt ratio for our mixes. You will refer to this a lot during your exam. You'll refer to this a great deal also during your testing and design. One important thing to note are the footnotes here at the bottom of this chart. It's there where you find that asphalt content is supposed to be at 4% air voids when we're doing these designs for surface mixes. There are special exceptions when we use polymer modified mixes. Also in base mixes there are differences there, so it's important to note those both for the exam and for when you're doing testing back at your own laboratory. So gyratory volumetric calculations. This is where we're going to we've actually done our testing in the lab, we've done our pills, we've done our rice, and we're trying to calculate in each of our blends what's our VTM, what's our VMA, what's our VFA. One of the things that you will see on your software that your gyratory compactor prints up is a gyratory curve. And basically, this is a curve that plots density according to gyrations on the gyratory compactor. This axis here is your percent density, and this axis here is your number of gyrations. So obviously, as we have more gyrations, we're going to have greater density. There are three different components of this that we're going to talk about: in initial, in design, and in max. In initial is a tenderness check, and this was utilized by VDOT, still utilized by FHWA, and this represents the mix during construction. And the thought is that if you achieve too much compaction too fast or too high a density too quickly, that it may be an indicator that this mix could be prone to rutting. In design is a volumetric check. This is basically what we do our gyrations to currently with VDOT. In most surface mixes, it's 50 gyrations. That gives us our in design. So that's our volumetric check. That's where we're checking air voids. This represents the mix after construction and initial traffic. In max is one that we no longer use. When superpave first started, we were gyrating pills up to 125, 110 gyrations, and that was to represent basically a rut check. And mixes that they got less than 2% air voids under traffic were thought to be a potential rutting issue mix. So that's not something we utilize any longer. It's still something we teach because it is part of the FHWA specification, but is no longer in VDOT specifications. This is the formula by which they calculate the densification of the specimen. We're going to be doing some of these shortly in the math. This is our Power 45 chart that's got all three of our blends posted up here. Blend 1 is that finer blend. If you remember, it's the virgin mix blend that we had put together. It's a little bit on the fine side of the curve. The second blend is this blend 2, which is on the low side of the curve. This is the one I think that has 10% wrap and fully manufactured sand in it. And then the blend that's running right through the middle is blend 3. And this is the one that's got 25% wrap in it. It's got both natural sand and manufactured sand. So you can see all of them are running through the wickets of the control point, so that looks good. These all work as trial blends for a 12.5 millimeter nominal size mix. So this is what a trial compaction chart may look like from your gyratory compactor. And basically what you have is our gyrations here. Here at 7 gyrations, we're up to 89%. Used to be the maximum tolerance for an initial. And here we are at in design, we're wanting to get 96%. So we're hoping to be around this line. And this is going to plot a line here. And ideally, we want to be below this for our tenderness check, below this intersection here. And we want to hit this intersection right at 96% density or 4% air voids. So here's specimen 1 of trial blend 1. And as you can see, we are lower than that 89% for in initial, which is a good thing. So our tenderness check checks out. We're also a little bit lower here for our density. So instead of being 96% density, it looks like maybe we're 94, 95% density. So here's specimens 2 and 3, and it looks like all 3 of them, and that's good. We've been pretty consistent with our compaction. It looks like they're all running just a little bit on the looser side of 96% density. So is the binder content high or low? Well, in superpave mix design, we're always trying to adjust our trial blend back to 4% air voids. So in this case, if this is 4% air voids, the only way to get these up to that point is by adding asphalt. We've got to tighten it up a little bit. So in this case, the 5.5% liquid that we've selected for our trial blends is a little bit low. We're going to have to add more liquid to move these lines up. So here are our 3 trial blends. What we were just looking at was 3 specimens from the first trial blend. These are actually trial blends 1, 2, and 3. And you can kind of see where they plot, and it makes sense that they would be all over the place because we've got 3 different, very different gradations with 3 different materials. Remember, we had a pretty coarse graded design, we had a fine graded design, and then we had one that runs pretty much through the middle, right through the restricted zone. And again, this is something that will be plotted by your software. I think this is right off of Pine Pave's software. This is what that chart looks like on their software. So how do we choose? Well, first we need to adjust all of our results to reflect 4% air voids and in design. Again, we selected an asphalt content at 5.5%. Now we've got to take our volumetric properties. We're going to manipulate that asphalt content so that all of our trial blends are hitting 4% air voids. Then we can select which one works the best for us. So here's trial blend number 1. Again, we were a little bit low, we were a little bit loose, so we've got to add some liquid to move that line up to this intersection. Trial blend number 2, we're actually a little bit tight. See, if you notice, we're up here, we're probably, if this is 96%, we're probably 97%, so it looks like maybe we're around 3% air voids. So the way we get that line to come back down, we're going to lower asphalt a little bit. Trial blend number 3, we're almost hitting it right on. It's pretty close. So we're not, and apparently we're just a little bit tighter. We've got our line coming down. I think the air voids on trial blend number 3 were 3.7. So we want to loosen that up just a fuzz to get us to 4.0. So here's a summary of our tested properties. We've got trial blends 1, 2, and 3. Remember, our trial blends are always done at the same asphalt content. We've selected 5.5% for our asphalt content. Number 1, remember this is our virgin mix, was a 4.7 on our air voids, 16.9 on the VMA. That looks good. It's a 15 minimum. 72.2 on VFA. Our FA ratio looks good. We're within our range. Our GMM at initial is under 89, which is good. That 89 max is still just more of a, it's more for guidance. It's not used any longer as a specification by the department. Trial blend number 2, that one we're a little bit tighter, so we're at 2.3% air voids. Our VMA is at 15.3, which is within the, we're not at the minimum, but we're pretty close. VFA is out, which makes sense. We're a little bit tight, so that usually is going to get thrown out. FA ratio is good, and we're at 90. So we're, you know, this is giving us maybe an indicator this could be a little bit of a tender mix. Trial blend number 3, we're at 3.7, we're pretty close to our 4. We've got a nice VMA here of 16.2. We're in the middle here on VFA, or at least within the range, and right in the center on our fines to asphalt ratio, 88.1 at initial. So I feel like all of these actually pass the initial stage, but what we've got to do next, we've got to figure out what will these mixes be. If we change these all to 4% air voids, what's it going to do to our liquid, and then what's the most appealing mix for us to use? So to do that, we've got to estimate the properties at 4% air voids. We've got to, once we move those to 4% air voids, it's going to give us a new estimate for binder content, a new estimate for VMA, a new estimate for VFA, a new estimate for GMM at an initial, and that's going to give us a new fines to asphalt ratio. If you have any questions at this point, please refer to your class proctor.